Welcome back, everyone. Today we are going to look at STP operations. Previously, we looked at the overview of STP spanning tree protocol and how it basically works. So in this lesson, we are going to concentrate on STP operations. Using the spanning tree algorithm, the spanning tree protocol builds a loop-free topology in four-step process. Firstly, all the switches will elect the root bridge. And then, after the root bridge is elected, they will now elect root ports on each switch, and also designated ports, and finally, alternate or block ports. So these ports are very important in how they play a role within STP. During STA and STP functions, switches use Bridge Protocol Data Units or BPDUs to share information about themselves and their connections to the other switches. BPDUs are used to elect the root bridge, the root ports, the designated ports, and also the alternate ports. Each BPDU contains a bridge ID or BID that identifies which switch sent the BPDU. The BID is involved in making many of the STA decisions, including root bridge and port roles. The BID contains a priority value, the MAC address of the switch, and an extended system ID. The lowest BID value is determined by the combination of these three fields. Bridge priority is the default priority value given to all Cisco switches and is usually 32768. This is the default value. So the range can be anywhere between 0 to 61440 in increments of 4096. A lower bridge priority is preferable. A bridge priority of 0 takes precedence over all other bridge priorities. Extended system ID is a decimal value added to the bridge priority value in the BID to identify the VLAN for this BPDU. Let's say the priority is 32768 and the switch is in VLAN 1, so now the extended system ID would be 32769. MAC address is the physical address of every device. Now, when two switches are configured with the same priority and they have the same extended system ID, then the switch would look at the MAC address to identify which is the lower BID. The switch with the lowest MAC address value, expressed in hexadecimal, will have the lower BID. So this is roughly how the BID is set. We have the bridge priority, 4 bits, extended system ID, 12 bits, and the MAC address, 48 bits. All of these makes the bridge ID. So let's look at the steps in STP operation. First, electing the root bridge. The STA designates a single switch as the root bridge and uses this switch as the reference point for all path calculations. Switches exchange BPDUs to build the loop-free topology, beginning with selecting the root bridge. All switches in the broadcast domain participate in the election process. After a switch boots, it begins to send out BPDU frames every 2 seconds. This is the default value, 2 seconds. These BPDU frames contain the BID of the sending switch and the BID of the root bridge, known as the root ID. The switch with the lowest BID will become the root bridge. At first, all switches declare themselves as the root bridge with their own BID set as the root ID. Eventually, the switches learn through the exchange of BPDUs which switch has the lowest BID and will agree on one root bridge. This is one election that is done very peacefully. So in this example, we have 3 different switches, S1, S2, and S3, and as you can see, the priority of these switches are different. S1 with the lowest priority, 24577, is elected to become the root bridge, even though his MAC address is higher than the other 2 switches. So priority comes first. Because the default BID is 32768, it is possible for two or more switches to have the same priority. In this scenario, where the priorities are the same, the switch with the lowest MAC address will become the root bridge. The administrator should and can configure the desired root bridge switch with a lower priority. In this example here, all the three switches have the same priority. Now, once everyone has the same priority, to elect the root bridge, they will look at the MAC address. Now here, the MAC address of S2 is the lowest compared to S1 and S3. So S2 will be elected as the root bridge. Now that you have elected the root bridge, you have to determine the root path cost. When the root bridge has been elected, the STA starts determining the best path to the root bridge from all destinations in the broadcast domain. The path information, known as the internal root path cost, is determined by the sum of all the individual port costs along the path from the switch to the root bridge. When a switch receives the BPDU, it adds the ingress port cost of the segment to determine its internal root path cost. This is similar to how in dynamic routing, they determine how many hops to go to a certain destination. The default port costs are defined by the speed at which the port operates. The table shows the default port cost suggested by IEEE. Cisco switches, by default, use the values as defined by the IEEE 802.1d standard, also known as the short path cost for both STP and RSTP. RSTP is Rapid Spanning Tree Protocol. So if you see here, different link speeds have different costs assigned to them. And the cost between STP and RSTP is different. But what you take away from here is that the lower the link speed, the higher the cost. Although switch ports have the default port cost associated with them, the port cost is configurable. The ability to configure individual port costs gives the administrator the flexibility to manually control the spanning tree path to the root bridge. So if you want to control the network, you can actually configure the port cost on a switch. Now we're going to look at step 2, which is electing the root ports. After the root bridge has been determined, the STA algorithm is used to select the root port. Each non-root switch will select one root port. What it means is, in this example here, this is the root bridge, right? So S3 and S2 are non-root switch. So you have to elect a root port on switch 3 and a root port on switch 2. The root port is the port closest to the root bridge in terms of overall cost to the root bridge. This overall cost is known as the internal root path cost. Let's look at S2 here in the example. There are two paths to go from S2 to the root bridge. Path 1 goes directly, the cost is 19. Path 2 goes from S2 to S3 and then to S1, and that will cost 38. So of course, because path 1 has a lesser cost, this interface or this port would be elected as the root port. Same goes for S3. Path with the lowest cost become preferred and all other redundant paths are blocked. After you have elected root ports, you now have to elect designated ports. Every segment between two switches will have one designated port. The designated port has the best path to receive traffic leading to the root bridge. What is not a root port or a designated port becomes an alternate or blocked port. All ports on the root bridge are designated ports. This is because the root bridge has the lowest cost to itself. Of course, the cost to itself is 0. Switch 1 is the root bridge. So every port is a designated port. If one end of a segment is a root port, the other end is the designated port. So this is one segment. This end is a root port, the other end is a designated port. This end is a root port, the other end is the designated port. Yes, of course, this port is also on the root, making it designated port as well. But assume that if you have a larger topology, if one end is the root, the other end is a designated port. All ports attached to end devices are designated ports. If you see here, this is a designated port. These, although not labeled, are also designated ports. On segments between two switches, where neither of the switches is the root bridge, the port on the switch with the least cost path to the root bridge is a designated port. So here, S3 and S2 are both not root bridges. So here they have to determine which one would become the designated port. If they have different cost to the root bridge, then the port with the least cost path to the root bridge is taken as designated port. When both switches have the same path cost to the root bridge, the spanning tree algorithm will use the bridge ID as a tiebreaker. The lower bridge ID wins. Now we look at how the alternate ports or the blocked ports are elected. If a port is not a root port or a designated port, then it becomes an alternate or backup port. Alternate ports are in discarding or blocking state to prevent loops. What it means here is that it doesn't forward anything. It gets information and then it drops it. It doesn't forward. It knows about things, but it doesn't forward anything. So alternate ports are in discarding or blocking states. And this is done to prevent loops. If you remember from the previous video, if we don't shut down this redundant path, possibility of broadcast storms, of loops happening is very high. Here in this example, the STA has configured port FO2 on S3 in the alternate row. Because this is the designated port, this one becomes the alternate port. So this port, fuzzy Ethernet 02 on S3, will be in the blocking state and will not forward Ethernet frames. All other interswitch ports are in forwarding state. This is the loop prevention part of STP. So every other ports in here will be able to forward ports, but this port would only receive but not forward anything. So what happens when there are multiple equal cost paths? How do you elect a root port? When a switch has multiple equal cost paths to the root bridge, the switch will determine a port using the following criteria: the lowest sender BID, the lowest sender port priority, or the lowest sender port ID. This is an example of the lowest sender BID. This topology has 4 switches with switch 1 as the root bridge. For S3 and S4, these ports have been elected as a root port because of the cost path towards the root bridge. S2, unfortunately, is having a dilemma. Which way do I take? Because this path is the same as this path. So which path will be elected as the root port? The bridge ID or the BID of S3 and S4 will be used to break the tie. This is known as the sender's BID. So S3 has the BID of 32769 and then all 5s, and S4 has 32769 and then all 1s. So of course, S4 has the lower BID, and then this port in S2 will be elected as the root port. In lower sender port priority, like shown in this topology, there are 2 switches, and the switches are connected with 2 equal cost paths between them. S1 is the root bridge, so both of its ports are designated ports. S4 has 2 ports with equal cost path to the root bridge. Because both ports are connected to the same switch, of course they have the same PID. So the first step is the tie. So the next step is to look at the sender's port priority. The default port priority is 128. So both ports on S1 have the same port priority. This is also a tie. However, if either port on S1 was configured with a lower port priority, S4 would put its adjacent port in forwarding state, meaning that in this example, both of these ports have the same priority. But in case one of them have a lesser priority, let's say for this particular port, the priority is 1 to 7, then the adjacent port in S4, which is F06, will be put in forwarding state. The other port, which is F05, would be put in a blocking state. The lower sender port ID. This is the last tiebreaker that can be used. This is the same topology as before. This is the root bridge, so both of these ports are designated ports. So which one of these would be the root port and which one would be the alternate port? In this case, when the port priority is the same, the decision is based on the sender's port ID, not the receiver's port ID. So because port ID of F01 is lower than F02, the port F06 will become the root port, and then F05 will be put into the block state. This is an example of a show spanning tree command in a switch. You can see that there is VLAN 1, right? And then the root priority is 32769. And then you have that this bridge is the root bridge. You can also see that the different interfaces within that switch have role. All of them are designated ports because it is the root bridge. So all of the interfaces have the role of a designated port. The status for all the ports are forwarding. And then here is the priority number. If you look here, there is subtle difference in their priority number. For interface 1, the priority number is 128.1, interface 2 is 128.2, and so on. And because this switch is a full duplex switch, so all of the interface types is point-to-point. For STP convergence, it requires 3 timers: the hello timer, the forward delay timer, and the max age timer. The hello timer is the interval between BPDUs, how long between one BPDU and the next. By default, it is 2 seconds, but it can be modified to be between 1 to 10 seconds. The forward delay timer is the time that is spent in listening and learning state. What is this listening and learning state? When a port is set to the blocked state, it doesn't do anything, it doesn't forward anything. But when a path goes down and the block state is to be activated, it doesn't activate directly. It would first go into listening and then learning state before it is upgraded to be the forwarding state. So how long would you be in the listening and learning state? That time is given by the forward delay timer. The max age timer is the maximum length of time that a switch waits before attempting to change the STP topology. The default is 20 seconds but can be modified to be between 6 to 40 seconds. The default times can be changed on the root bridge, which dictates the value of these timers for the STP domain. So here, again, the show spanning tree command. Let's look at the red highlighted font. We have the hello time or hello timer, which is 2 seconds. The max age timer is 20 seconds, and forward delay time is 15 seconds. All of this are set to the default. STP facilitates the logical loop-free path throughout the broadcast domain. The spanning tree is determined through the information learned by the exchange of BPDU frames between the interconnected switches. If a switch port transitions directly from the blocking state to the forwarding state, Without information about the full topology during transition, the port can temporarily create a data loop. For this reason, STP has 5 port states, 4 of which are operational port states, and 1 is called disabled and is considered non-operational. Forwarding state is when a port is forwarding. It receives BPDUs, it sends BPDUs. Blocking state is when it doesn't forward any BPDUs. Let's say there is an error or problem in the network and this block state needs to be unblocked. It first goes into the listening state, and then after that it will go into the learning state, and then it will become the forwarding state. The blocking state, it just receives BPDUs, it doesn't forward any data frames, and it doesn't update its MAC address table. Listening port state, it receives and sends BPDU, but there is no update in the MAC address table and there is no forwarding of data frames. Learning port state, it receives and sends BPDUs, there is an update in the MAC address table, but it doesn't forward data frames yet. Forwarding state, it receives and sends BPDU, it updates the MAC address table, and it forwards the data frames. Disabled port state means it's disabled, it is not operational. So none of these things are happening. In a VLAN environment, there is such a thing called per VLAN spanning tree, or PVST. STP can be configured to operate in an environment with multiple VLANs. In per VLAN spanning tree versions of STP, there is a root bridge elected for each spanning tree instance, meaning that each VLAN can have its own root bridge. This makes it possible to have different root bridges for different sets of VLANs. STP operates a separate instance of STP for each individual VLAN. If all the ports on all the switches are members of VLAN 1, then there is only one spanning tree instance. So that is the end of STP operations. We have looked at the steps taken for STP to work within a network. By default, STP is set in Cisco switches, but you do have to understand its working so that you can be a better administrator. Until the next lesson, goodbye.